Hi, my name is Stephen Mcgroarty and I'm a software engineer here at Graphcore. I'm here today to present Poptorch, Graphcore's PyTorch framework, on behalf of the whole PyTorch team here at Graphcore. So let's meet the IPU. Graphcore was founded in 2016 to develop a new kind of processor just for AI. We call it the Intelligence Processing Unit. Each IPU is built up from 1,472 independent processor tiles, each directly connected to each other by ultra-fast on-chip interconnects. Here you can see one of these 1,472 processing tiles. Each tile is a pairing of 6 threads of dense floating point compute and a large, low-latency memory cache. By keeping the memory as close to the compute as possible, we dramatically reduce the energy cost and massively improve the performance when compared to traditional memory access to DRAM or HBM. The tiles are arranged in columns up and down the chip in these dense banks of memory plus compute. The remaining space in between the tiles is dedicated to direct core-to-core connections, meaning any core can write to any other core, and all cores execute this transfer in parallel with all other tiles. This moves the memory to exactly where it is needed at exactly the right time. These core-to-core connections give us high energy efficiency and lightning-fast bandwidth by having the compiler calculate the synchronization and communication logic and embed it directly into the final binary. This gives the IPU this incredible on-chip bandwidth, coupled with huge compute potential, since 100% of the chip silicon is dedicated to just machine learning. PyTorch is implemented for the IPU via a simple wrapping framework called Poptorch. Poptorch allows developers to run models for both training and inference on the Graphcore IPU. It's part of our wider software ecosystem, the Poplar SDK, which was co-designed from scratch with the IPU. By wrapping your existing PyTorch model in a Poptorch annotation wrapper, we can convert that model into a Poplar graph, which will take full advantage of the hardware. Poptorch and Poplar will automatically optimize memory placement for maximum performance while minimizing memory utilization. Let me share some examples with you. Here you can see a super simple example running on CPU. We have a fully connected layer taking in some random data of the same shape as an MNIST image. With just 2 lines, that model can be converted into a computational graph, compiled with Poplar, and will automatically run on IPU. And one of those lines is just an include. Okay, so that's inference. For training, let's first look at the anatomy of a simple PyTorch training example on CPU. On the right, you can see our tiny MNIST model expanded to now train on some actual MNIST data. So we first zero the gradients, as usual in PyTorch. We call the model and we get our predictions. The loss is typically outside the model, and the PyTorch user manually invokes backpropagation on that loss as the starting point for gradient descent. Finally, we step the optimizer, and that applies the calculated gradients to the weights. In Poptorch, we abstract this. Since the IPU is a graph processor, we want to represent the entire computational graph, including the backward pass, as a single fused graph. So forwards and backwards can be compiled and optimized together. To begin with, we just wrap our model in a training wrapper, and this is basically the same as the inference case, but this time we use the training wrapper specifically, and we provide it with our optimizer. A small conceptual change is that the loss is now part of the model itself, and by extension, part of the graph. When we call the model, we are now invoking the full computational graph. Backpropagation and optimizer application are part of that graph. These were applied automatically for you by Poptorch behind the scenes. To show what we mean by computational graph, let's look at the default execution scheme, sometimes referred to as eager mode. In eager mode, the CPU will call each operation as it appears in the model, going through the dispatch system to eventually invoke the accelerator kernel. This means that each call has a degree of CPU overhead. Sometimes the accelerator can block the CPU completely while it is executing, and a lot of the time the accelerator will just sit idle, waiting for the CPU to tell it what to execute next. Static graphs solve these and other bottlenecks. Firstly, the CPU overhead is reduced to near zero. This is because we no longer dispatch each call. Secondly, there is no delay between invoking the kernels, as the IPU is driving its own execution rather than waiting on the CPU. Thirdly, with the complete context available, many graph and compiler optimizations become available, which allows Poplar to accelerate the model. On the topic of reducing host overhead, if you look at our current graph, it probably looks something like this. Since this tiny example is so small, we're spending all of our time on the CPU just waiting to call the IPU. Instead, we can let the IPU drive this process. With a tiny change to our model, we can have the IPU automatically pull in the next batch of data when it needs to be executed, which minimizes the time that it is idle. We provide the small option structure, which can be passed into our wrappers to configure the IPU execution and compilation. The option in question here is device iterations. It tells the IPU how many samples it should process on each call of the model. What this does is this partitions the data along the batch dimension, requiring that more data be pulled in. To avoid the user having to provide more data manually, we provide a simple wrapper around the normal PyTorch data loader, which when given the option, will automatically pull in the correct amount of data without changing the user's batch level within the model. Each of these options operate in exactly the same way. Device iterations lets the IPU drive the pulling in of each batch of data. Replication factor automatically parallelizes the model over multiple IPUs using data parallelism. Gradient accumulation just accumulates the gradient as you would expect, but when pipelining, it also increases the depth of the pipeline, which improves performance efficiency. Okay, let's look at a more complex model. So we're going to show a BERT medium from Hugging Face running on IPUs. Here you can see this is just an off-the-shelf BERT model. We've embedded this model as part of a normal Torch module. We use all the normal Hugging Face encoders to encode a question about Scotland. As before, we just wrap the model up in our inference wrapper. We call it as usual. Then we have some normal Hugging Face post-processing steps to convert our tensor predictions into text. Afterwards, this will print out Edinburgh, which is the answer to the question. In this whole example, there's only one line which is actually IPU specific. By providing just this wrapper, you'll automatically capture the transformer graph and compile it for IPU. When that is next invoked, it will run on IPU. Finally, I'm happy to say that Poptorch has been integrated by the team at PyTorch Lightning. This enables even easier access to run PyTorch models on GraphCore hardware. Here you can see a PyTorch model being offloaded to 8 IPUs using data parallelism automatically using PyTorch Lightning. The only IPU-specific change here is IPUs equal 8 in orange. The full set of Poptorch options are still exposed by PyTorch Lightning. These can be directly passed in to expose additional IPU-specific functionality. We have a number of resources on our website, including benchmark results, source code, extensive documentation, and a large number of tutorials and examples. This includes our PyTorch Lightning port of Computational's KRNN. In this case, you can see it here generating brand new Shakespeare. Thank you very much.